What is it?
Right. Books.
Good morning, everyone.
Good morning, sir. So, sir, we'll start the talk in few minutes.
Yeah, that's fine. That's fine. So, how are things in India right now? Is it still pretty bad regarding this
So
COVID
it's,
situation?
yes, sir. But
Okay.
in Niger, it is quite better than around situation. And how is the situation there?
It's getting better here because I guess most people, no, not most, but half of the population got shot. So, it is getting better here overall.
So, did you
Yeah,
get vaccinated?
yeah, a long time ago in
Okay.
February.
Okay.
So, it's getting better here for that reason. We were pretty bad in December and January, those 2 months. But afterwards, they're getting better a little bit. Yeah.
Yes. Hello. System change. Hello.
Yes, I
Yes.
think we lost connection a little
Okay.
bit. Yeah.
Yes.
Okay.
Sir, you just check with your PPT so whether you can able to share the things or not. Hello, sir. I would like to request you to check the with the PPT whether you are able to check able to share your screen or not. Sir.
Yes.
Sir, just check with your PPT whether you are able to share the PPT or not.
Okay, good. Let me do that right now. I will
Yes, sir.
start sharing my screen.
Yes, sir. Yes.
Okay, share screen. And then let's see. Can you see all of that?
Yes, sir.
Same
Yes,
slide?
sir. I can see your PPT.
Okay, so I will leave it like that. I will leave it like that now.
Yes, sir. Sure, sir. So can you please change the slides?
Change the slide, okay.
Yes, sir. Yes, sir. Yes, sir. It is fine. Totally fine.
Yeah, okay. I'll go back. Okay.
Yes, sir. Hello.
Yep.
Yes, sir. Sir, Soumya will give a brief introduction of yours, then we will start the talk.
That's fine. Yeah, that's fine.
Okay.
Hello everyone. Myself Soumya Mishra on behalf of Niger OSA Student Chapter, welcoming all of you to the second talk of this colloquium organized on the occasion of International Day of Light. And it's my great pleasure to welcome our speaker, Professor Govind Agrawal, into this session. So let me give you all a brief introduction about him. Professor Govind Agrawal received his MS and PhD degree from the Indian Institute of Technology, Delhi in 1971 and 74 respectively. After holding several positions at the Polytechnic Paris, City University of New York, and AT&T Bell Laboratories, he joined the University of Rochester in 1989 as a professor of optics, where he later received the first doctorate and professorship in optics in 2013. Professor Agrawal is a life fellow of IEEE and a fellow of the Optical Society of America. From 2008 onward, he has served on the editorial advisory board, and from 2014 to 2019, he was the editor-in-chief of the Advances in Optics and Photonics. Professor Agrawal received several prestigious awards for his remarkable contributions to teaching and research. He received the IIT Delhi Distinguished Alumni Award 2000, IEEE Photonics Society's prestigious Quantum Electronics Award 2012. He was the recipient of 2013 William H. Ricker University Award for graduate teaching. Professor Agrawal was awarded the Esther Hoffman Baylor Medal of the Optical Society in 2015. He was the recipient of two major awards in 2019. One is Max Born Award of the Optical Society and Quantum Electronics Prize of the European Physics Society. Professor Agrawal is an expert in several areas of optics, such as fiber optics, nonlinear photonics, quantum optics, silicon photonics, and optical communications. He has authored more than 450 research papers in journals and written several books which are used worldwide for teaching and research. His book on fiber optic communication system is a standard graduate textbook used in many universities for courses on telecommunication. Another book on nonlinear fiber optics, which currently appears in the top 10 most cited books in physics. So it's my honor to welcome once again Professor Agrawal for the talk titled Space-Time Duality in Optics. So I request Professor Agrawal to kindly share his screen.
Thank you, Soumya. That's a nice and long introduction. Thank you very much. So first of all, I want to thank the organizers for inviting me for this talk on the International Day of Light, which happens to fall on Sunday, but that's not a problem. I think we are all fine with that. We are scientists. We work every day, so we are okay with that. All right. So with that, let me say that my topic today is something my group has been working on for about 5-6 years now, and its title is Space-Time Duality in Optics and its Applications. So before I tell you what space-time duality is, let me give you a little bit of a historical introduction. And so I should say that space-time duality was first noted in the 1960s by a French scientist Tournois and a Russian scientist Akhmanov. And there are two references by these people in 64 and 69. But then nobody took it seriously. And then in 25 years later, in 1989, temporal imaging with the time lens was first discussed. So that was a first time people tried to use this idea to something interesting. And more recent work has focused on applications such as temporal waveguiding, that's from our group, and ultra-fast time holography, and you will see some other applications as I go along. I will tell you some other applications of this. And finally, I should mention that the application of space-time duality has been discussed in a tutorial by Alex Gaita's group at Columbia. And that is this is a reference for that paper. In case you want to learn more about it, this is like a tutorial, so you can learn more with that. So let me then go to my first slide, kind of, which says what is space-time duality? Why we are interested in that? So first of all, what is it? Well, it results actually from a mathematical equivalence between spatial diffraction of beams and temporal spreading of pulses in the optical media, just such as glass, for example. So we know diffraction in one transverse dimension, for example, is governed by what is known as the paraxial equation. If you do any course on optics, you see this equation, and it has only one parameter, k, which is the propagation constant, depends on the wavelength of light. Otherwise, this equation tells you how a beam will spread in space. Now, if you go back and look into, try to do something in waveguides and ask how does a pulse evolve inside a waveguide? So this is optical pulse, and its evolution is governed by an equation which looks almost same in form. So if you look at that, there's a lead first order term in distance, and the second order term is now in time, not in space. And there's a single parameter again coming in, which is we call as a group velocity dispersion parameter. So this is a dispersion parameter which comes in. So what you can say from this similarity is the slit diffraction problem is identical to the pulse propagation problem. Now there's a difference here, which we'll see later on, makes a difference. You see sign is positive here, sign is negative here. But beta 2 can be positive or negative. Beta 2 can have either sign. K, of course, is always positive because it depends on wavelength, cannot change. But beta 2 can be positive or negative. So you can see that this is actually more general. You can have more variety in the pulse case. But when beta 2 is negative, then these two equations become identical. Okay. So what we can say, many results from diffraction theory can be applied to optical pulses. That is basically what it says. That if you can do something in space, you should be able to do in time, and vice versa. I mean, that is the idea. So this is a very simple idea. It's a mathematically sort of similarity of the equations on which this idea is based. Okay. So, so let's ask ourselves, the first thing we can say, we know what a lens does. A spatial lens in space is, as everybody knows, it looks like something like this. So here's my lens. A beam comes in. So some kind of plane wave is coming in here, let's say. Or a Gaussian beam can come in. And then this lens is going to focus this beam down. So its size narrows down. And after some distance, when it focuses, it starts spreading again. So essentially, a lens is trying to focus down a beam, if you want, and before it spreads again. So why is lens doing that? Lens is doing that because thickness is different in the center and at the edges. And because of different thickness of the material, you end up putting a phase shift in space, x, if you want, in this x direction. You put a quadratic phase shift on the, so this is a phase front. You curve the phase front if you want. Plane with phase front comes here, and wave front comes curved afterwards. So that's what lens is doing. So if you want to do something in time domain which works like a lens, you want to make a time lens, what we call a time lens, you want to do something similar. So I can now write down something in time. So my output field in time after my time lens will depend on the input field by this factor. So what is this? This is a phase factor which varies with time. So in other words, different parts of in time of the pulse, different part of pulse will have a different phase shift. So it's a curved wavefront in time, if you want. That's what we are doing. So basically, if you anytime you can multiply by this kind of phase factor, a quadratic phase factor, we can call that device acting as a time lens. That is the idea. And as here you see focal length of the lens f comes in, one parameter. There is one parameter here we call df here for the same reason. This is the parameter that is a kind of x as a focal length of the device. Now, of course, units are different. Its unit of this quantity is second square, picosecond square, something like that. But it's x like a focal length, if you want. Okay. So that's the idea. Okay. So what can we, first of all, we can ask, how can we make such a quadratic phase shift in time? And one way to do that would be simply use a modulator, a phase modulator. What is a phase modulator? Well, basically, it's a electro-optic material. An example would be lithium niobate. and you can apply a voltage to it. If this voltage changing with time, so you're applying a sinusoidal voltage to this material, the refractive index also starts changing in time, same way. And because of that, what is coming in at the input end, when it comes out, is phase is modulated. So output wave is phase modulated. And how is the phase is modulated? Well, it's very simple. If you are doing a cosine sinusoidal modulation, you will multiply the phase factor, but have a cosine omega mt, where omega m is the frequency of modulation. At the frequency at which you're modulating this modulator, that's the phase. Now you would say, well, this doesn't look like to a quadratic phase at all, right? And you're right. It's not a quadratic. However, if optical pulse is much shorter than one modulation cycle, what I mean by that is if my optical pulse sits somewhere here, something like this. This is my pulse is just sitting in somewhere here. Then what matters is only this region here, around here. And this region is a parabola. You can expand cosine in a Taylor series, for example, you will get a quadratic term, something like this. So for a short pulse shorter than the modulation cycle, I can expand this cosine and claim that this is acting like a lens. And this parameter df I mentioned, which is kind of focal length, you can calculate from here, is given by this quantity. So that means you can control the focal length of the lens by changing the amplitude or end frequency of phase modulation. So you can create a time lens, and you can change its focal length by just changing the modulation parameters, essentially. So that's the idea. So this is very simple. I mean, having a modulator in the lab is easy to find. So we can do that. This can be done easily. So that is one way to make it. But there are other ways to do it. And let me discuss those. You can also do this. So here is a general summary. How can you make a time lens? Techniques for making a time lens. Well, we want to have a quadratic phase shift. A quadratic phase shift is equivalent to linear frequency shift. What I mean by that, if you take the derivative of the phase, the delta omega, which is frequency shift, varies linearly with time. So if any time you can make a linear frequency shift on the pulse, then you can say you're making a time lens, basically. So many nonlinear techniques can provide a linear frequency shift. For example, crosswave modulation by a parabolic pump pulse will create a linear frequency shift. So that will be a time lens, for example, can be used that. Even each of Gaussian pump pulses in the normal dispersion region of a fiber can produce a quadratic phase or a linear frequency shift. And also Fourier mixing inside a silicon waveguide can also be used for this purpose. So many groups have used nonlinear effects to create a time lens. And it's possible because all you want to do is create a quadratic phase on the pulse. Okay, so that is a, all right. So now we can see how we can use it to applications. So we come to application a little bit. So first thing you can ask yourself, well, we know what we can do with a normal lens in space. In normal lens in space, you can focus light. So if a beam comes in, you pass through a lens, it focuses down to a small size. So you can compress a beam, make a short beam. That means you should be able to compress a pulse by using this technique. So let's say there's a long narrowband pulse, and I want to compress it. That means I want to focus it down, just like here. So focusing in space, here I want to do focusing in time. So I do a time lens. That means again a modulator if you want, putting a quadratic phase on the pulse. So that's my time lens. Now I have to propagate into space here. So in a diffraction case, you're propagating in the space, which does the diffraction. But now to do this free propagation, I have to put a dispersion. So I need to put a piece of fiber. A dispersive medium could be a piece of optical fiber. So I can take my modulator and put a piece of fiber next to it and fix the length right. Then I can focus the pulse down to a short pulse right here. It's just like a focusing of the beam. I'm focusing a pulse to something very short. So that's the one application, that by making a time lens, you can compress a pulse by a large factor, by the way. This could be quite large. So that is very interesting. And it's not very, you can see it's not very difficult to do. It seems simple. So, yeah, so now you can say, well, if this is the idea that I can do, perhaps I could also do temporal focusing and imaging. So focusing we did, I want to do imaging. Imaging means I want to image some kind of time trace, some sort of time, something rapidly varying in time. I want to image that in the output, and this image could be magnified if you want, just like a image can be bigger or smaller. So there's a magnification here which could be controlled through my imaging system. How do I image it? Well, idea is very simple. You again use a lens, so there's a time lens, and now I need to propagate the light in a dispersive medium before and after the lens, both time. So I put a piece of fiber over here, another piece of fiber here. I adjust the length right. That is like making the imaging distance correct. And I have to use some sort of imaging formula to do that. And if I did that, then I should be able to image this pulse, this input into something which is a stretched version of the same thing coming up. So what you might say, well, why it is useful? Well, it is useful because if this is varying very rapidly, you can't actually measure it because they are not very, detectors are not very fast. You can't measure things easily if something changing in time very, very fast. And fast, I mean picosecond or femtosecond time scale. You can't measure it on a detector. But if you can stretch it by a factor of 10 or 100, then you should be able to put it on a detector and measure the same thing. So if you use the magnification factor, then you exactly know what your input signal look like. So imaging could be used for measuring these things in time. And it turns out that this is actually very simple, similar to what you have in space. Just like in space domain, you have a formula called 1 over u plus 1 over b plus equal to 1 over f. You get a similar formula here in time domain, which says 1 over d1, which is like 1 over u plus 1 over v over here, and then this gives you 1 over f. And these are the equations, and these parameters depend on the dispersion of the fiber, length of the fiber, d1, d2, and df, of course, depend on the modulation parameters that you're going to use. So as long as you satisfy this condition, you can do imaging. And imaging means that you can create the same signal, but stretch it or compress it in time. So that's imaging. And that is very useful also. There's a lot of application as such. Okay. So that's interesting. And of course, we can do imaging. You can make what we call a temporal microscope. That's simply imaging system. There's nothing new here. Same way, just like a microscope, you can take an image and you can make an inverted image here. Similarly, here you can have this timeline. You can have an imaging system here, which will create an inverted image. Inverted image means what was ahead will become behind, essentially. So you will reverse in time. Here you're reversing in space, you reverse in time, same thing. So you can see that because of this space-time duality, we can duplicate or copy each feature of this from space to time by learning this idea of the time lens. And that is the point here. Now here's something else people thought for a while. If you know in space, we can do something what you call 4F processor. Some of you may know what it means. It means simply use two lenses. Rather than using one lens, you use two lenses, same focal length. You put one object at the focal point of here. This is the object or image, some kind of image, something you can put here. And then this is the second focal, here what you make the image. So it's object and image. And then in the middle here is what we call a Fourier plane. That means at this location, what you have is the Fourier transform, whatever was here. Lens does that for you. A lens can create a Fourier transform. So this is where you get a Fourier transform. So now you can do processing. What I mean by processing is you can put some kind of phase or amplitude modulation here. You're modifying the spectrum, if you want, of the spatial frequencies. So modifying them in the can change the image. So you can make image better. You can improve the image by doing this kind of Fourier processing. So this is a very popular technique in the space domain. So you might say, well, maybe I can duplicate this in time. And of course you can. So what you will do, this lens is this lens, this lens is this lens, this propagation here is a piece of fiber. This distance here is again two pieces of fiber or one piece of fiber over here. And then there is a final, this distance is again. So you are having a several dispersive media thing, but it's duplicating all the structure, and this will work same thing exactly. That means in the middle here, you will make a Fourier transform of this time signal. In other words, you get the spectrum of the whatever you are putting in, the spectrum will be created here. Now you can put some kind of apertures here to modify the spectrum, and that will change things in time domain. So that is what we call a 4F processor. Now I want to tell you that this looks like that this is a very complicated thing to do. So it turns out in time, you can simplify this design a lot. In fact, so much that you don't even need a time lenses. You can simply do the following trick. And this is where things become very interesting. You can actually take some kind of time domain signal here at this end, pass it through a long piece of dispersive medium, a long piece of fiber, for example. You have to make sure the dispersion here satisfies this condition, that the dispersion is large enough that this is correct, this happens. And if that happens, what will happen is it creates a Fourier transform by itself. You don't need a time length. Just a dispersive medium can create a Fourier transform. I will show you in a minute how it does it. And then once you do your processing here, you take another dispersive medium, but now you change the dispersion from positive to negative. So this is minus D to the plus D2. And this will convert another inverse Fourier transform and bring you back to time domain. So in other words, you can do Fourier this processing without using any time length, just two pieces of fiber with opposite dispersions. And this is amazing in some way that you can do such a simple thing. The reason we can do that in time, because we can have a dispersion which can change sign. In space, we cannot do that because in space, we have only one, K can only be positive. Lambda cannot be negative. So we could not do in space, but in time, we can do that. So this is actually simplifies this design a lot by doing this way. So let me first explain to you how by passing something through a piece of fiber can create a Fourier transform. It may sound surprising to you, but in fact it's not. And I want to show you that in the next slide. And you should remember this again from your diffraction theory. If you have done optics, you probably know. So in optics, if you have done this, you know that if you suppose you have a slit, okay, and you're looking at the diffraction pattern created at this end. In the far field, what we call in optics far field, means distance is large compared to what is known as the dispersion length. If distance is large compared to diffraction length, if this condition is satisfied, then what you get here is a pattern that's a Fourier transform of the input pattern. This is very well known. The far field diffraction pattern is a Fourier transform of the input signal. So in other words, the Fourier transform of this function is created here by itself in space, of course, not in frequency domain, but it mimics the shape. It's the same shape. Okay. So you're creating a Fourier transform basically here. So that means that's what we can do in time. I can have a dispersive medium. I make sure its length is long enough that this condition is satisfied. Then if I put a rectangular pulse here, and its spectrum will be the sine x over x sinc function, what we call this end. So this is my input in time. This is my frequency. Now I go through this dispersive medium. What will happen here? Well, in time now, my shape will look like a spectrum. And the spectrum will not change, by the way. Spectrum does not change in a dispersive medium. So this spectrum will remain as it is, but the shape will also look like a spectrum. And now you can modify this spectrum by doing some kind of blocking certain parts or something like that, and go the inverse Fourier transform, and you will get a different pulse shape. So you can modify pulse whatever you want by changing its spectrum in some way. So this is the idea that in other words, a dispersive medium, a long piece of dispersive medium, X is a Fourier transform. Now this is very strong, very, very interesting idea. Has lots of applications, and I want to show you some of these applications. So here's what happens. I mean, if you think of this about is how it is working, this is what is happening, that you put a pulse here, and this is my fiber, which is dispersive element, let's say. So my light is going through this inside. Now, as light goes through inside, the fiber will chirp the pulse. It's known that a fiber, because of dispersion, it starts chirping the pulse. What it means is that different frequency component of the pulse will go to different times. So essentially, the spectrum is being rearranged inside it in time. But by the way, this is in time. But the shape of the pulse is changing. And by the time you come at this end out here, it is becoming exactly what the spectrum of this pulse was. That's what the shape is becoming. So it's constantly evolved inside the fiber until it becomes just like at the output, a Fourier transform. This is a very simple way to understand that. And so long fiber, broader the short pulse, this pulse will get very broad compared to this, and produces output that mimics the spectrum of the input pulse. This is called DFT, or dispersive Fourier transform. If you search the literature, you'll find hundreds of papers on this topic. And it is also known as time stretch transform. And you may say, well, why would I do that? Because I can always use an optical spectrum analyzer in my lab to take a spectrum. What is the big deal if I get the spectrum in time? And you may think that there's no big deal, but turns out it's a big deal. Why? Because your optical spectrum analyzer in your lab does not take the Fourier transform single pulse. It takes a long time to make that spectrum. So it uses hundreds of pulses. It sort of averages out things out. So you only see an average spectrum. You do not see the spectrum of a single pulse. So the spectrum is changing from pulse to pulse. You can never see them on a spectrum analyzer. You can never see that. So in this case, we are creating a single short spectrum. Okay, that is the main thing. It allows to study spectral change in real time. Okay, that means I could use it for applications such as sensing and medical imaging, because I can see what is happening in real time. I can see the lab on my oscilloscope because I can see the spectrum over there. I mean, so it can tell me that. So this can be used for many, many applications, this idea of DFT. Let me show you two applications. All right, so let's see I want to, I have a sample that I want to make an image of that, in fact, even movie eventually. So I can make a time-dependent changes. And I want to see what kind of molecules are here. My sample is whatever it is, I want to image it, then I want to know different molecules that are here. So I start with a very short pulse. It's a very wide spectrum. So this is femtosecond pulse with wide spectrum. This pulse goes through the sample. When it goes through the sample, different molecules absorb different wavelengths. There are lots of wavelengths here, but different molecules absorb different wavelengths. So you will encode the structure of this molecule into the spectrum of the pulse, because somewhere you will have lots of absorption, other places you have less absorption. So effectively what is happening is the entire structure, the sample image is imaged into wavelength domain in the spectrum of this pulse here. Now, all I have to do is measure the spectrum. So I put a fiber, a dispersive element, and convert my time pulse shape in time that mimics the spectrum. Okay. Now I can put in a photodiode and measure it. Now imagine this thing was moving. So if the molecules are moving, that means this pattern will change in time. As this pattern changes in time, I should be able to measure it. That means I can make a movie of this moving image of the sample by this technique. And you cannot do this any other way. It's a very interesting way to make do imaging, medical imaging. So this is very powerful. Okay. Other application very similar to that. You can think of it's like a sensor or sensing application. So I again start with short pulse, wide spectrum. And now, let's say I want to change the shape of this pulse to something I want. This pulse is, let's say, is a very short pulse, a Gaussian shape or some shape pulse. I want to convert this to a very funny looking shape, some shape, weird shape. How would I do that? Well, I can do this very simple. I can say whatever shape I want, I take a Fourier transform that will give me the spectrum I want. So now I use a spectral filter. A spectral filter will simply reshape the spectrum to the spectrum I want. So whatever spectrum I want, I use a filter to convert this spectrum to the spectrum that I want. And then I use a piece of fiber to encode that spectrum in time domain. So that means now my time domain shape is exactly what I wanted, if you want. So that is the idea of this one. So those are two applications you can do in this case. So I think that gives you some idea of the applications of this idea of the time lens you can do. So now I will tell you something that my work, we have been doing my group for a while. And this is an idea of what I call temporal reflection and refraction. Okay. So to understand that, again, go back to a space domain. In space domain, you have a interface here. So this could be air on the left here. On the right could be glass, for example. And let's say a beam comes in at some angle. And this beam, of course, we know as it hits the interface, it will get reflected partly and partly get transmitted. And the angle will change. The angle change of this one, angle change of this one. So, but the frequency will not change. So in the space domain, when a wave comes in, angles of the wave can change. What it means is that the momentum can change, because the momentum is the vector k vector. Momentum is h bar k. K is the propagation vector. And so when I'm changing angle, I'm changing k vector. So I'm changing the momentum of the photons, but I'm not changing the energy of the photons. So in a spatial interface, I can change the momentum of the photon, but not the energy of the photon. And that's because a spatial discontinuity means that momentum is not a conserved quantity. In quantum mechanics, we know that X and P are related, right? Now in time, T and omega are related. Frequency and time are related in the same way. So that means if I have a time domain interface here, interface in time, then if my something comes up, when you hit this interface, its spectrum will change. Its momentum will not change, photon momentum will not change, but photon frequency will change. So this is what I mean by that. What I mean by temporal reflection is not really reflection itself. It's a spectral changes produced by the interface. So it's a different kind of reflection you can think of. So reflection, so what is the temporal analog of the reflection and refraction? So as I said, at a spatial boundary, frequency is preserved, but momentum can change. At a temporal boundary, momentum is preserved, but frequency can change. So a change in angle at the spatial interface translated to a change in the frequency of incident light. And so by reflection, I mean, I'm going to change the spectrum of light. Okay. So what it means is a pulse will break into two pulses. A reflected pulse that will stay on this side of the medium, the spectrum will be different, and a transmitted pulse that will go to the other side of the medium with a different spectrum. So that's what we will try to see in a minute. That's what happens. So that is the change difference. There's no angle involved here, only spectrum or frequencies involved in this case. So this is our idea. When we thought about it a while ago, then we thought, okay, let's see what does it mean? What will it do in general? Okay. The problem, of course, is, so here is showing you something similar, that in space, I think it's a repeat of the same thing. In space, when I come in, my angle is here, it changes to theta r and theta t over here. In time, I will come in, omega I, omega r, omega t. Now, you might ask yourself, what I mean by changing refractive index in time? What I mean is that if I have a medium, some kind of medium, and this medium has some refractive index N1, and then as light is propagating in the medium, at some time suddenly I change the refractive index N1 to N2 everywhere in space. It has to change everywhere. I mean, so it's a very different kind of change if we were talking about. Change the refractive index suddenly from N1 to N2 everywhere in space if you want. And in that case, your frequencies will change, but so it looks like same. It looks like a reflection, but it means something different. So again, the bottom line is frequency conserved in space and the wave vector conserved in time, but frequency can change in the time case. That is the bottom line. Okay. Now it turns out that this is very hard to do because it's very hard to change the refractive index everywhere at the same time. So in practice, of course, you want to do a moving boundary. You don't want to do a static boundary, you want to do moving temporal boundary. So what I'm saying now is there's a temporal boundary that will travel forward at some speed. So I'm creating this index change, but index change is not stationary, it's moving. And the pulse is also moving, but they can move at different speeds. So they can catch up if you want. So everything moving forward, nothing moving backward, but they're moving at different speeds. So the pulse goes faster than the boundary, pulse will catch up with the boundary and we'll see the boundary as such. So it turns out it's best to work in a moving frame in a boundary stationary. So we make the transformation. We go to a time which is in which boundary is stationary if you want. So this T is a time where boundary is stationary. And so if this is the picture in the lab frame, the picture in time in the frame of the boundary stationary becomes just like reflection, as you expect. But everything moves forward, nothing goes backward. It looks like it's coming backward, but it's actually moving forward too. That is something you have to keep in mind. So that's what we'll see in a minute. Okay, so the first thing we do, we want to see how can we see this effect on a computer first of all. So let's assume optical pulse is propagating inside a waveguide with some dispersion relation, and the temporal discontinuity at some time. If we want to incorporate them into our model, so what we do, we expand this beta omega in a Taylor series. So that's a dispersion term we include. two of them. Notice that this is delta beta 1 mean is relative to the pulse speed. And then at the end here, we put this Heaviside theta function, a Heaviside function, which means that there's no index change for t less than TB, but it is index change after TB. So this is sudden change in time, index is changing. So the beta is changing, or refractive index is changing. So that is my sudden change in time. And this is what we want to use. So what is beta B? Beta B is just K0 delta N. Okay, but delta N is index change I'm going to do. We'll see later on that this index change I will make is not very large. We'll ask about temperature change of 10⁻⁶ or 10⁻⁷. Not very large changes. So we have this special relation. We can use it to investigate what happens to a pulse when it arrives at the boundary. So we did that. To do that, we got an equation which you can get from this special relation. And this equation you get is actually looks very simple. So this is the equation that governs what happens to pulse at a temporal boundary. And so you can solve that on a computer. We use a Gaussian pulse, let's say. The pulse width is 1 picosecond, and boundary is located at 5 picosecond away. Now, of course, they're moving at different speeds. There's some dispersion. So these are some realistic number. And so we use a beta B, this index change of this amount. Now, if you use this relation and take a wavelength of 1 micron, then this change corresponds to the refractive index change of 10⁻⁷. So we're not asking very large change. Small change in refractive index at some time suddenly. And this we'll see later on, you can do nonlinearly. You can create through nonlinear effects. So that's what we will do. We make a small change in the refractive index at some time. And so we go back on the computer, solve this equation, and see what we get. And let me show you what we get. What we get is exactly what you would say we call it is reflection or refraction. So here's my boundary. Here's my Gaussian pulse, which is moving at different speeds. So it's sort of really approaching the boundary. When we approach the boundary, we see that part of it gets reflected over here, and part of it gets transmitted, as we expect. So this is what happens in the frame. Is the boundary stationary. Now reflection here is not very large. If you look at the number here, it may be 1 or 2% reflection, and 98% is being transmitted. But effect is there. Now, if you want to see what happens in the spectrum domain, so the spectrum, what happens in the spectrum? This is input spectrum here in the top. That's the input spectrum. As you hit the boundary, the spectrum starts shifting. It shifts in two ways. It creates this reflected wave over here. So the spectrum of the reflected pulse, and this is transmitted pulse. So you can see that we said before that in the boundary, the spectrum changes, frequency changes. So that's what is happening. So energy is being transferred from here to here, and some energy also goes over here that creates the reflected pulse. Now, why does it move slower here, or can it stay here? Because if you change the frequency of the pulse, group velocity changes, speed of the pulse changes. So these two pulses will not travel the same speed. That's why this is traveling different speed than this one right here. So that's why you see that they suddenly, so this appears to move backward, coming back in the same medium. It can never cross the medium. It's really a reflection. It never crosses the boundary because it's being reflected if you want. So it is a kind of reflection, but it's not angle dependent. It's a frequency dependent reflection. Okay, so that's what we see. So that's the prediction of the model. I mean, you get simple model we make, you can predict that. So this is a same thing I want to show you in a what we call spectrograms. The spectrograms are nice because you can show the spectrum and time at the same time. So this is the time here in time, and that's the frequency. An input pulse looks like a bullet here. So this is like a bullet that basically says there is some spectrum and some width to the pulse, and together they make this little bullet with a peak intensity middle. And then this pulse is moving towards the boundary. Boundary is located somewhere here. You will see it's like right here somewhere. Somewhere there's a boundary. So this is moving towards the boundary, start moving, and now it start hitting. Here's the boundary, and immediately you can see that it creates a transmitted pulse here, a reflected pulse here. And you can see spectrum is shifted. The spectrum here, this one is shifted only a small amount, but this was shifted by 2 terahertz, for example. So it immediately creates two pulses if you want with different spectrum. And as you cross bound more and more, you can start seeing. And at the end of the day, when you have left the boundary, then you have this is a transmitted pulse. Looks almost same, little different width. And then this is reflected pulse, which is coming over here. And you can see this is going this side, and this is moving backwards as such. So this is a same simulation what I showed you before, but now showing you different frames. You can make a movie out of it if you want. That looks pretty good. Okay, so that's basic idea. Now, other thing we can ask ourselves, can we predict how much frequency change takes place? The answer is it can be done because you can actually impose this condition momentum conservation. So what is the idea here? This parabola here is the dispersion curve before we change the refractive index. So before the boundary, and after the boundary, this green curve is the dispersion curve. Now every frequency, if you look at this frequency here, for example, because the beta remains same, I cannot change this line. I should stay on this line. So that means this particular frequency will get shifted to this frequency here, or this frequency here. Not to this one, because this is for physical region, its slope is different, so it does not allow that. So only allowed thing to shift it here, and this is a transmitted pulse, or it can shift here, and there's a reflected pulse because it still remains in the same medium. You cannot go here because this pulse will move backward in the transmitted medium, and that's not possible. So you end up getting these two solutions over here. And once you know this, you can actually do the math very easily. It's not very hard math to do, to calculate how much shift you do, how much it depends on that. I'll just show you the results here, but you can go through this dispersion relation, and you find that the reflected pulse shift is given by this. So frequency shift you get, a reflection is controlled by delta beta 1 and beta 2. So as long as you can calculate, you know these parameters, you know how much frequency shift you get. And this shift is typically large. It can be 10 terahertz, that means 100 nanometer shift. So it could be large shift. And that is, so reflected pulse get a large spectral shift. And transmitted pulse get a much shorter shift. Again, we can calculate it from this quadratic equation, solving this equation, and this is the answer you get. And only plus sign corresponds to physical solution, as I mentioned. Minus sign you have to ignore here. So we get that here. So if we can, what I'm showing you, you can calculate the spectral shift for the reflected and transmitted pulse by using the requirement, the momentum is conserved. That's what we are doing here. Okay. So basically you can calculate these quantities. Okay. What else we can do? Well, we can ask ourselves, is there a total internal reflection? Is it possible that there will no light will go to the other side? Everything will go to the remain on the side it came in, and we know it happens in space. Space cases happen. You have to go from high index side to low index side, and then it can happen. And we know the condition from Snell's law. So this is the condition for this to happen. So that is essentially what we know from in space. In time, it can also happen. But for this to happen now, we have to say there is no transmitted wave. That means this omega t should not exist. In other words, if this thing does not exist, then a transmitted wave cannot fall. So you can see from here, if this quantity is larger than one, then this becomes negative. And hence this frequency becomes imaginary. And because of that, this frequency cannot exist. So this is the condition for total internal reflection in our time. So we can find a very nice condition for the total internal reflection from our formulas. And so then we said, can we see that on a computer from our modeling? And so we went ahead and tried to model that, and this is what we get. And so again, it's exactly what you expect. A light comes in and it hits the boundary, and then it gets totally reflected. And the spectral domain, input spectrum, once it's the boundary, shifts by large amount, in this case, shifting by 6 terahertz. It comes from here and shifts by 6 terahertz and going over here. So we have a huge shift, spectral shift, and the pulse remains to the same side. So that is the total internal reflection. And this it shows it happens. Now you might say, well, how much index change you need to get this? And the answer turned out to be in our formal model or for our parameters, I need an index change of 10 minus 6 to obtain the satisfy the TIR condition. And so that's something one could do. It can happen. So then we ask ourselves, if we can total the reflection, well, let me first of all show you something interesting here. So total reflection, we ask ourselves, is there a temporal analog of the evanescent wave? We know in the case of space, light should actually go to the other side, but just decay exponentially. And so we magnify that image I showed you previous page, and we do see a little leakage on the other side. So this is an evanescent wave. So this is essentially exists. Then we can also do frustrated total internal reflection if you want to do that. That's possible. Also, you see this fringe pattern here, which is, you wonder where it's coming from. It's coming from because my frequency of this wave and that waves are different. So there is interference between these two waves. And these are the fringes coming because of the interference between them. So that's the reason for that. And so you can say the fringe spacing here in time is inverse of the frequency shift. So that's what we see. So all of this is easily understood, basically. And I think finally I could show you something in the spectrogram, same thing. So now we have an index change enough for total internal reflection to take place. So you can see that this pulse, like a bullet, is moving towards the boundary, hits the boundary, and immediately starts creating this reflected wave. And everything is by now transferred over here. And this is my reflected pulse, and it sort of goes backward, as you see here. So it's what you expect. Nothing crossed the boundary, basically, as you see here. Okay, so that's all very simple. Couple of things we try to understand was, one was that what happens if there is a higher order dispersion in the system, third order dispersion. So far we included only two terms, beta 2. Beta 3 is not 0, I have to include the cubic term. If I do that, my dispersion relation becomes very different. So this is before the boundary, and after the boundary is the green curve. So a couple of cases I'm showing you how. So this is quite different. So that means there could be more than one solution. You can see here now sometime you may start getting, because it's bending a lot, you may get more than one transmitted wave or more than one reflected wave. And again, computer simulations show that is the case. Let me clear this up first of all. So here's an example of that if you go here, you may create two transmitted wave, one reflected wave. In some cases, you may create two reflected waves. Here there are two reflected waves, for example. So everything is possible, because of the higher order dispersion into the problem. So this will be, the higher dispersion becomes important for short pulses. If your pulse is shorter than 1 picosecond, then you have to worry about it. If you have dropped more than 1 picosecond, you don't have to worry about that. Okay, so the final topic I wanted to cover today was temporal waveguides. So now that we have seen that total reflection can take place, so I can make a waveguide. That means I can have a situation where I have a lower index here and higher index over here and here. So I have a lower index valley, if you want. Now you notice that from the space case, this can never happen. In the space case, you have to have your core layer or waveguide layer must have a higher refractive index for TIR to occur. But in our case, because our beta can be positive or negative, beta 2 can be positive or negative, it's possible that my core layer can have a negative index change. And I still can make a waveguide. So that's interesting, first of all, first thing. So here I have a region here, I have a temporal window if you want. This is a temporal window in which the refractive index is lower than outside. And we ask ourselves, is it possible that if I put a pulse here in this window, this pulse will never escape this window? It will stay confined inside. In other words, it can go to this side, but hit, come back, hit, do something like that, but never go outside this window. It's basically, it's a waveguide, and waveguide confines the pulse to the temporal window because of total internal deflection. Right? That's what we're asking. Is it possible or not? So we looked into that. And first of all, we ask ourselves, are there temporal waveguide modes? We know the spatial waveguides can find the modes. Can I find the temporal waveguide modes? And believe it or not, we found that it works exactly the same way. You can find the modes of temporal waveguides. Number of modes depends on a parameter we call the V parameter, just like in spatial case. This V parameter, of course, definition is different, but depending on this V parameter, you get more and more modes. Here, example of a first mode, second mode, third mode. So you can see that each time you have mode, you get more fringe-like pattern. It's like a spatial case pretty much, and you get more spectrum gets more than one peak in this case, which you expect when reflecting for that reason. So we are showing you 3 modes of 20 picosecond wide waveguide. V equal to 55. Of course, there are many more modes. So first of all, what interesting was you can find the modes of these waveguide, which was sort of nice to see that. And then we ask ourselves, can you make a single mode waveguide? So here's the example single. So we are asking ourselves that this is my window, which is my waveguide layer if you want. And this is my cladding layer on the top and bottom in some way, analog of that. And then I'm coming here with a short pulse. And the short pulse goes and it starts spreading, you expect. It just as a medium pulse spreads. But once it spreads, part of it leaks out, but then it becomes confined. So a short pulse, 2.5 picosecond in this window gets confined, but lose some energy. And this is because it's what we call mode matching. The spatial waveguide, then my pulse width did not match to the shape of the waveguide. And hence I'm getting this some losses. So if we increase the size to 5 picosecond, this input pulse width, now I have almost completely nicely fits into that. And you find that very little leakage takes place, although the entire energy is confined to the waveguide. So you can make a single mode waveguide out of this very nicely. Of course, you worry about the mode matching, but whatever comes in the input, how nicely it fits into the waveguide. And that's just like a spatial waveguide. So there's nothing new here. It sort of shows that everything which happens in space can happen in time. And then finally, you expect to see some kind of zigzag pattern if you have the parameters right. So here I have 1 picosecond Gaussian pulse trapped inside a 10 picosecond waveguide. And these are the parameters we are using, which are realistic parameters. And you find what happens now, of course, this is what you expect. The pulse is traveling at different speeds, so it starts hitting the boundary. Once it's the boundary, it gets reflected. So the spectrum changes. So you see there's a spectrum change suddenly. It's the boundary, spectrum shifts by a large amount over here. And then, so this pulse is a different spectrum than this pulse. So now it's a different spectrum. And once it's here, then spectrum goes back. So here, again from here, we go back to where we were. So, this one and this one and this one have the same spectrum, and this and this and this is a different spectrum. So basically you have two pulses, two sets of pulses with different spectra. And each time they go back and forth, but as light is trapped. Its pulse never escapes. It just goes, hits each side and comes back. So that's kind of multi-mode waveguide we expect to make this way. And it seems to work. So finally, and this is something we are doing now, is can we see it in the lab? This kind of stuff. So we need 2 moving boundaries to make the temporal waveguide. We need 2 moving boundaries. How can we do that? There are 2 ways you can do that, we think. You can use a microwave signal to change refractive index inside the electro-optic modulator. So you have electro-optic modulator, you can apply a voltage, rect shape voltage pulse, and that within that voltage, where you're applying a voltage, in that duration, the index will increase. So you will have a high index region if you want, and then you can try to trap a pulse inside that region. So that's one way to do it, would be to use electro-optic modulator. Problem here we find, we have not done the experiment yet, that modulators are not very long generally. The modulators, the total waveguide length is maybe 5-6 centimeters. And it's very hard to have everything done in that short distance. So that's the problem with the distance here, how far you can travel. And of course, the other problem is that the speed of the microwave and the optical wave, they should be different but controllable. And that's something we need to figure out. Now, other technique which we think is very practical is a crossband modulation inside a nonlinear waveguide through an intense pump pulse. So what we are saying here is we send a pump pulse into the fiber, for example. This pump pulse will create a high index region inside the pump pulse only through Kerr effect, through the nonlinear Kerr effect. So we can create a moving boundary, moving boundary inside the pump pulse, or we can use 2 short pump pulses to create 2 boundaries. 2 ways you can do that. And then you can put a probe pulse between these 2 boundaries and show that under some condition this will remain confined. So we went ahead and tried to simulate this on a computer, if this is really can be done or not. So let me show you some of the results we have for that. So here, first of all, this one shows you that you can have a reflection. So I have a Gaussian pulse. Here's a 40 picosecond super Gaussian pump pulse. That means a rect shaped pulse. So pump pulse is traveling, is not really changing width because I'm assuming that dispersion is 0 at this wavelength. And the probe pulse comes in, and the probe pulse then hits and gets reflected, and you can see that it can reflect very easily. And you can get total internal reflection also possible here. So clearly we can do that. So question can be trap the pulse in some way to make a waveguide. This is again showing the same thing. I can do the same kind of thing with short pump pulses. So this is short pump pulse, active propagated soliton, and then my probe pulse will get reflected from this. So again, something we expect. And finally, we want to make a waveguide. And so this is the waveguide we are making now. We are saying that I have a pump pulse, 20 picosecond pump pulse. It's a blue curve here. And then it's a 10 watt peak power. So it's peak power high. I'm assuming beta 2 is 0 at this wavelength. So that means the pump pulse does not change the shape, but it propagates at certain speed. A Gaussian probe pulse, 8 picosecond, which you see inside here, has some wavelength shift of 3 nanometer. So has some value of the dispersion at that point is moving, is also going within this pulse. And so now we can be, what we find that you expect something like this. We were able to do that over 4 kilometers of fiber. So length of the fiber was long, but we were able to make it and make it work in that fashion. So this, I think it's possible, and that's where we are going. We are going to do in the lab, and this is a single mode waveguide also possible to make as we expect. So that's again possible. So I think my time is running out. So let me conclude with all this I have told you. So this is a short summary. So first of all, I hope I have convinced you that space-time duality is a simple concept with many applications. In other words, very simple idea. When you look at the idea, you think, oh, it's obvious, but what we can get out of that. But it turns out when you start looking into it, it becomes very useful, lots of applications. It can be used for temporal imaging, for making time microscope. We've showed you that temporal equimotor internal reflection can occur for optical pulses at a moving temporal boundary. And I hope I showed you and convinced you in the temporal case, frequency shift plays the role of angles. In other words, in the spatial case, the angles are changing. In the temporal case, frequencies are changing. We have identified conditions under which an optical pulse can be confined within a temporal waveguide. We have shown you that. Most of such waveguides were also found. A single mode condition was identified with this D parameter. And finally, I showed you the pump probe configuration can be used to make such waveguides through a nonlinear phenomenon of crosswave modulation. As I told you, this is what we're doing in the lab right now. We're trying to make a temporal waveguide by using these ideas. So with that, let me stop at this point. I think I've reached the end of my slides. So make sure yeah. Okay, so I think I will stop at this point and take any questions you might have.
Thank you very much, sir.
Yes.
So now the stage is open for questions.
Yeah, at least there's some kind of echo on your side. Something is going wrong.
So the stage is open for the questions. Or ask. I think the question chat box. Actually, there are questions in the chat box.
Let me stop sharing and maybe go to the chat mode. Maybe I don't know. This looks like. Let me see if I stop sharing, because I can't. If you want to do the chat. Let me stop sharing. See. Yeah, let me see if there are any questions in the chat. Okay. So do you want me to read the chat and answer the questions as written there?
I can do that. I can read the question.
Okay. All right.
So the first question is in total internal reflection. Pulse looks propagating in backward in time. What does it mean?
I think it's hard for me to understand because your language, your voice is breaking up. So say it again.
In total internal reflection.
Yeah.
pulse looks propagating in backward in time. What does it mean?
No, so as I said in the early on, there is never backward propagation. In other words, it looks propagating backward in time in the frame in which the boundary is stationary, but the boundary is actually moving, and every pulse is moving in the same direction. All pulses are moving in the same direction, except they are moving slower or faster compared to the boundary. So anything moving slower compared to the boundary looks like moving backward. So it's because we are in a moving frame, we have to interpret our results correctly. In a moving frame, boundary is stationary. So if something is moving backward, that means it is moving with a slower than the boundary. And something which is moving forward in time is moving faster than the boundary. So that is the only thing we can say. So nothing actually moves backward, really, let's say in space or in time. It only appears to move backward. Everything is going in forward direction. So one way to think about it here is the pulse comes in and boundary is moving, pulse is moving faster. So it comes and hits the boundary. Now boundary, it hits the spectrum changes. One part starts moving slightly slower, so it never crosses the boundary. Other parts changes the spectrum, it travels faster than the boundary to go to the other side if you want. So that is what the picture is actually, but nothing moves backward.
Okay. There is another question. What happens to the polarization in temporal total internal reflection? Does it behave the same way as in the case of spatial?
Yes, that's a very good question. So far we are assuming here the polarization is same. Nothing happens to polarization because the refractive index. We are doing a scalar kind of theory treatment if you want. We're not looking at the vectorial case in this case. We're solving a scalar equation. So the question that one can ask is will the polarization will also change if there is a temporal reflection, for example? we have not looked into that yet very thoroughly, but initial indications are not. I think a scalar case is good enough, but we have not yet finished working on this.
There is one more question. Double refraction happens in anisotropic medium. What is equivalent media for time double refraction?
So as I showed you, that double refraction can happen in time if the pulse is short and third order dispersion is included in the model. So in other words, when we go beyond the second order dispersion or beta 2 parameter, what I call beta 2, which is second order dispersion. If I go beyond that, include third order dispersion, which becomes important for short pulses. So short pulses means a pulse which is less than a picosecond, so maybe femtosecond pulses going in the
So there is one more question.
Yeah.
I was wondering how we use this method to detect the gravitational waves produced via collapsing of space-time.
Let me see. I'm trying to see that question. I was looking. So, okay, here. So I was wondering how we use this method to detect the gravitational wave produced by collapsing of space-time. Oh my God, I have no idea. I don't know how to answer that question. I would have to think about it, but I don't know at this point. Yeah. There must be some way, but I don't work in this area, so I don't know that one.
There is another question. What type of simulation is performed in which platform language?
Okay, all right. So we are using the MATLAB. There's nothing special. We can solve that equation using what is known as the split step method. That we use for nonlinear problems. Same method can be used to solve these equations because it's actually equations look very similar to nonlinear problems. It's not that different. So we use the same split step Fourier method to solve the equation essentially. And it's done in MATLAB. We do in MATLAB just simply. Platform is our platform in MATLAB, but you can write code in Python. You can write code in Fortran if you want. Nothing is special here.
There is another question. How can we physically realize a temporal boundary?
Oh, yeah, sure. So temporal boundary, as I told you, there are two ways you can realize that. One way is to use a pump probe kind of situation, where a pump pulse is changing the refractive index of the medium through nonlinear effects. So you send a pump pulse, and wherever the pump intensity exists, the refractive index will increase through the Kerr effect, if you want. That's what is known as that. So you can increase the refractive index selectively in some region, in some time domain, in some time window, and a probe pulse can then see that change and get reflected out of that. So one way is simply you send a pump pulse and probe pulse together, but they move at different speeds, and you can arrange them so they hit each other, if you want, inside a medium. So that's one way to do it, very simple way to do that. The second way you can do it, as I mentioned near the end, was that you can actually use a modulator and then apply a voltage pulse to the modulator. And the modulator refractive index will increase within the voltage pulse time window. And that also can be creating a time moving temporal boundary. There are two ways we know we can do that.
There is one question. Focusing in time, does it mean we can achieve even shorter pulses? Current record being a few attoseconds. Defocusing, imaging, as you said, does it mean we will be able to capture image dynamics?
Okay, so if I understand the question is that can be first two questions. Can we compress the pulses by using this focusing idea, focusing by lens, can we compress the pulses? The answer is yes. By using focusing idea, compress the pulses. Second part of the question is how short you can make that pulse. Can you go below the below the signal period? Answer is no, generally no. Other things will happen. Other things will happen that will, like higher order dispersion and other. I mean, our model will not be accurate when pulse becomes very short. Some other thing needs to be taken into account. So generally, higher order dispersion will forbid to compress it to single cycle or shorter. But you can certainly take a 10 picosecond pulse and compress it to 1 picosecond. That's possible.
Soumik has raised his hand. Soumik, you can unmute yourself and ask the question.
Hello, sir.
Yes.
Yes, sir. I have a question regarding that 4F imaging in time. So in spatial domain, when we do 4F imaging, we use the aperture, spatial aperture, right, to separate out the high frequency component and to get a clear image. So in time, what type of aperture should we use?
Or in time, right?
Yes.
So, okay. So in time, so let's say you are doing a Fourier transform of the pulse, and you got a spectrum now in time domain after creating a dispersive Fourier transform, right? And you want to manipulate that, you want to put an aperture, right? That's what you're saying. And they basically, in that case, yeah, what I mean is that you want to sort of modify the spectrum in time, but you're getting the spectrum features, but displayed in time. And you want to do something so the spectrum is changing, right? That's what you're saying, right? If I understand.
Yes, yes.
Yeah, I see. Okay.
So
So
filter the image.
Yeah, so generally you will do again that using some kind of modulator or something, which is putting its own, which will put you can have a modulator which create a, for example, let's say you have a modulator that creates a pulse train. You apply a voltage pulses to the modulator. Every time you create a voltage pulse the modulator, your refractive index change increases. So you can create a pattern in time through modulator or in the time domain on the pulse. And this will be changing the phase of that spectral region. I mean, those frequency components will have different phases now, and that will do that. Now, if you want to change the amplitude, then you have to create some kind of fringe pattern in time, essentially. And that you can do by interfering two different frequency or two different signals in the modulator so that you have a high index, low index region, essentially creating a pulse train in the modulator. And that pulse train then will modify the signal you have. So you have to do something with the modulator, short answer.
So okay. I think there is no more question.
Okay.
So once again, thank you so much, Mr. Agrawal. Agrawal for giving a very informative and wonderful talk on such a fascinating topic. Also, we are very grateful to you, sir, for your valuable time out from your busy schedule. Once again, thank you. Thank you very much, sir.
Okay, well, thank you for inviting me. I enjoyed this meeting. I didn't see many faces, but I saw few faces. And I have never been to Niger, or I've not been to your institute actually in the past. I did go to Bhubaneswar about 12 years ago, but that time I think this institute did not exist. I think it's a new institute, right? When was it created?
2009.
2009, so I missed it by 1 year. I was there in 2008, and I didn't remember somebody even telling me that this existed at that time. But good, so I'm glad to hear and glad to see that you guys are very active in optics, doing this kind of things and arrange this meeting. So it's very nice, and
Thank you, sir.
hopefully we'll have a chance to meet at some point, right? Okay, all right.
Thank you,
Good
sir.
to you. Good luck to all of you. Bye.
Bye, sir. So, with this, we are concluding this colloquium. Thank you, everyone, for joining in this session.